Okay, so we already defined what a tangent is, but let's just jog our memory as to what a tangent line actually is. A tangent line intersects a circle at exactly one point, and that is called the point of tangency. So in the little illustration there, the point of tangency here would be point A. Now here's a special property about a tangent line. Not only does it just touch your circle at one point, it is perpendicular to a radius drawn to the point of tangency. And you can see that there in that illustration. AB is the tangent line, A is the point of tangency. If we draw a radius from the center to point A, the radius and the tangent line form a right angle. Now, because there's a right angle there, it means we're going to be able to use some right triangle properties. We're going to be able to use Pythagorean theorem and things of that sort. Okay, take the earbuds out, put the phones away. Please take notes. Examples 1 and 2. Okay, determine if AB is tangent to the circle. So if it is tangent, then it must satisfy the Pythagorean theorem. Okay, if it's tangent, it must satisfy the Pythagorean theorem. So we don't know for sure that we're looking at a right triangle right there, but we need to check it. So we need to see, does the leg squared plus the other leg squared equal the hypotenuse squared? Okay, so one of the legs is the radius, 8. One of the legs is the tangent, 15. The hypotenuse is what connects the other end of the radius to the other end of the tangent line. So we've got to see, using our calculator, does 8 squared plus 15 squared equal 17 squared? And in this case it does. Both values are 289. So yes, in this case, segment AB is tangent because the Pythagorean theorem is satisfied, so that means we do have a right triangle, which means that does form a right angle. It is perpendicular with the tangent line and the radius. Yes, sir?
So can we always check if it is tangent by doing this Pythagorean?
Yes. Yes. All right, so let's look at number 2. Okay, same deal here. It's just drawn a little bit differently. Okay, one of the legs is always the radius, so one of the legs is 11. The other leg is the tangent, and then the hypotenuse is that other piece. Now look at this picture. That 5, is that entire segment? No, that 5 is only this piece right here. Okay, the 5 is only from the outside of the circle to point B. How do we find the length of that whole thing? Add the radius. Look at this piece right here. What is that? That's a radius, right? So that part's 11, so the whole hypotenuse is 16. You will probably have to do that more than once on some of these problems, so just keep that in mind. The radius comes in handy in more places than just where it's drawn. So 11 squared plus 14 squared is 317. 16 squared, I don't believe is 317, no, it's 256. So those are not equal, so no, that segment is not tangent to that circle, so there is not a right angle there at A. There's not a right angle at A. Okay, let's look at the next little section. It says, if JK is tangent to circle L, find X. So it's saying, assume that JK is tangent to the circle. So we're going to assume that there is a right angle there at J. We're going to find whatever missing piece they ask us for. So the way that they have number 3 set up, 7 is our radius, so it's one of our legs. 19 is that tangent, it's our other leg. And they have the hypotenuse marked as x. So 7 squared plus 19 squared is equal to x squared. So let's find 7 squared plus 19 squared. Is 410 our answer? No, what do we have to do? Square root. Is 410 a perfect square? No, it is not. So we either leave it as the square root of 410, or if it's multiple choice, we look at our answer choices. No, it's not going to be divisible by 25. I don't even know if it's by 10. Well, it is divisible by 10, but 10 is not a perfect square. So I'm trying perfect squares. Obviously, it's not divisible by 100. I don't think it's divisible by a perfect square, unless I'm just missing something. I'm just going to leave it as the square root of 410. Okay, the square root of 410 is a hypotenuse. I was going to try and review reducing our square roots, but I don't think it's reducible. All right, let's look at number 4. Okay, again, we are assuming that that is a tangent line. So we're going to go ahead and draw in our right angle. This time, our radius, they give it to us, 11 squared. That's one of our legs. Okay, our tangent is x. So we square that. It's equal to our hypotenuse squared. Is the hypotenuse 7? No. If they don't put one of those lines like they have on number 3, indicating that that's that entire length, then you can assume it's just the smallest piece that it's next to. So that 7 is just that piece. So we need to move our radius, not move our radius, but apply the fact that the radius is 11, apply that to that other distance, so the hypotenuse is 18. Okay, we're going to do a little bit more work to solve this one. 11 squared, 18 squared, so 11 squared is 121. 18 squared is 324. Subtract 121. So x squared is equal to 203. Seriously doubt that that's perfect square. It is not, so we're going to write it as the square root of 203, and we're going to say that's also approximately 2.48. And go ahead and put a decimal approximation on that as well. And I do that because anytime I'm solving the Pythagorean theorem, I always want to look at the problem and I want to make sure that my answer makes sense. Okay, my x was one of the legs. So it's got to be shorter than the hypotenuse. Okay, if you get a decimal value right here for one of the legs that's longer than the hypotenuse, then that means you did something wrong in your calculations. One of the legs cannot be longer than the hypotenuse. It's an easy check just to make sure that you didn't make any mistakes in your setup. Okay. Let's look at number 5. Okay, number 5. We have a radius of 10. Okay, again, we're assuming this is tangent, so we're assuming that's a right angle. So our radius is 10, so 10 squared plus our tangent is our other leg, so plus 24 squared is equal to our hypotenuse squared. Again, they didn't label the entire hypotenuse, they just labeled part of it. So we've got to apply that radius. So our hypotenuse would be x plus 10. We got to add those two pieces together. And it's squared. So we've got 100 plus 24 squared is 676. Now, when we did these yesterday, I tried to emphasize the fact that we need to remember to FOIL x plus 10 times x plus 10. But because of the way that this is set up, technically we can solve this using square roots. Okay, since we've got x plus 10 squared, we can take the square root of both sides. So the square root of 676 is 26. The square root of something squared just leaves you with what was squared. So x plus 10 squared, you take the square root, square, and the square root cancel. And then we can subtract the 10. And that gives us 16. That way we don't have to worry about factoring. we don't have to worry about getting that extra answer. Remember, when we factored, one of our answers was always negative. Now, technically, we should get a negative answer here. When we took the square root, we should have considered the positive and the negative. So 26 minus 10 is 16. Negative 26 minus 10 is negative 36. That should have been our other option, but again, x was a length, so it can't be negative. So we really only need to consider that positive 16. And I would check that. I would make sure that when I put that x back in there, since it's part of my hypotenuse, that my hypotenuse is longer than the other two legs. So 16 plus 10 is 26. That is the longest of the legs of that triangle, so we're good. Bless you. Okay, number 6 is set up. Look, it looks a little different than the ones we've been doing so far. None of the points so far have involved a diameter, but that's okay because we still have a tangent. The diameter, part of the diameter is the radius, okay? So technically, a diameter can be tangent or perpendicular to your tangent line as well. So we still have the right angle there at J. So let's see here. This time our legs, we've got that x is one of our legs. So x squared plus, what's the length of the diameter from M to J? 22. Don't put 11 squared. 11's just from L to J. Okay, so you've got to include the fact that that's the diameter, so you've got to multiply it by 2 before you square it. And then the hypotenuse here is 25 squared. If you ever struggle with identifying your hypotenuse, I like to do this. Use your little right angle. Use the corner of that right angle. It points directly to the hypotenuse. Okay, so that's just a little trick if you struggle with identifying what is indeed the hypotenuse. All right. So 22 squared plus, or not plus, I just need 22 squared and I need 25 squared. I'm getting ahead of myself here. That's 484 and that's 625. So we need to subtract the 484. So that gives us what? 141. Did I do that right? Square root of 141, not a perfect square, so we are going to write it as the square root, and we are going to write down its decimal approximation. And that was one of my legs. It was, according to the picture, it was the shortest leg, and that does match up. All right, I'm going to skip 7 and 8 and 9. Let's look at where it says more tangent line properties. It says if two segments from the same external point, so in that diagram, B is that external point. Okay, B is the external point, a point out external. That means you're outside. So you're outside the circle. B is the external point. Two segments. We've got two segments coming from that point. We've got BC and we have BA. They are tangent if they are tangent to the circle. So if we have right angles at A and C, then those are congruent. AB and BC, or CB, however you want to say it, have the same length. So if they are tangent, then they are congruent. Vice versa. If they're congruent, then you know that they're a tangent. Okay, so you got to be able to use that property there and apply that. Then we have this other one. It says if a polygon is circumscribed around a circle, then all sides are tangent. Okay, if a polygon is circumscribed. So a polygon, many-sided figure. Okay, so in this case we have a triangle, but you could have more than a triangle. All sides are tangent. So this is going to use the property that we just learned. If they're tangent, then these pieces are congruent. Now, they're not all congruent to each other. I think it's pretty clear from the picture here. But BD is congruent to BE. EC is congruent to FC. and AD would be congruent to AF. Okay. Circumscribe means think about a circumference, or if you circumvent something, you go around it. So if you're circumscribed, that means something is drawn around the circle touching. Okay. All right, so let's use these properties. It says in the directions, find each value or measure, assume that segments that appear to be tangent are tangent. So if it looks like it just touches the circle in one point, then it just touches the circle in one point, and it does form a right angle. So we can use these properties. So in number 10, A and C appear to be tangent points, and they are. So that means that these two segments are equal to one another. So all we do is set those expressions equal to one another, and they want us to find x. So we're going to solve for x here. We subtract 5x, so that gives us 3x minus 19. Add the 19, that gives us 42. And then divide by 3. So what's that, 14? 14 is equal to x. Number 11, they want us to find PQ. P and R appear to be points of tangency, so they are. So that means these two segments are equal to one another. Let's start by finding x, and then we will find what we really want to find, which is PQ. When we subtract the 8x, we get 6x minus 13 is equal to 5. Add the 13, it gives us 18. Divide by 6. That says x equals 3, but they didn't want just x. They want PQ. PQ was the 14x minus 13. So plug it back in. 14 times 3 is 42. 42 minus 13 would be 29. Okay, number 12. Number 12 has a few more lines drawn in there, so let's see if that even comes into play or not. They want us to find SV. So SV is this segment right here in the middle. So that has nothing to do with the fact that these two segments are equal to one another. Okay, those two segments themselves are not going to give us SV, but that's the only other information we're given besides the 17. So let's start with finding out what x is. So those two segments are equal to each other, so we can set their expressions equal to each other, so we can solve. So we get 8 for x. We don't want just x. So these segments, they appear to be tangent. So we're going to assume that they are tangent. So at T and at U, we have right angles. We'll look at what other information they gave us. They told us what the radius was. They said the radius was 17. We're trying to find this segment in the middle. Well, based on what we did on the front side, wouldn't that be the hypotenuse of that right triangle? Okay, so we found x. Let's plug x back in so that we can find st. So 10 times 8 minus 41, 80 minus 41 would be 39. So this segment's 39. The radius is 17. We can set up our Pythagorean theorem to find, I'm going to label the SV there with an X, to find what that truly is there in the middle. So 39 squared plus 17 squared, 1810. Hopefully you definitely know that's not the answer. We got to take the square root. That's approximately 42.544. if we check it, makes sense. Okay, that is longer than the two legs, 39 and 17. 42 is longer, which it should be because it's the hypotenuse. All right, almost done. Look at 13 and 14. So we're using the properties. It says that if that polygon is circumscribed around this circle, then its tangent, okay, we form tangent lines, so that means these segments are equal to each other. So if from H to E is 16, then from I to E is 16. If from D to G is 11, then from D to H is also 11. If from F to I is 9.5, then from F to G is also 9.5, and wants the perimeter of the triangle DEF, so we just need to go through and add all those values, or we can multiply by 2 and add them together. Whoops, multiply 9.5 by 2. 11 times 2. Okay, so we get 73. So it's not too complicated when they set it up like that. Let's look at number 14 though. Okay, number 14 has some different measurements in there. They give us like from P to Q, that whole side, but then they also give us some pieces. Okay, so break it down into pieces. If this is 23, then this piece is 23. If the whole thing was 37.5, then what's the distance to Q? Or how do we find the distance to Q? Subtract. So 37.5 minus 23 is what? 14.5? Okay. If that's 14.5, then this piece is 14.5. And we got 27.1 right there, so this is also 27.1. We need this part. We know the whole, 52.5 minus 27.1. I really don't want to mess that one up. 52.5 minus 27. 25.4. There and there. Now we can find the perimeter by just adding up all those values. 23, we've got 2 of those. We got 2 of the 14.5. We got 2 of the 27.1. And we got 2 of the 25.4. So that gives us 180 for that whole quadrilateral.